Right. Okay, so in this video I want to discuss the Proj construction, which is something which creates spaces in algebraic geometry which are similar to projective spaces, but it's something I didn't understand for a long time. And so in this video, I'm going to talk about how you can view the Proj construction as something relating to a GM action um, on a space. Um, And so I made another video on how to view GM, and which is like the multiplicative group of units in algebraic geometry, and how to view that as acting on a space. Um, and it turns out that the weird things of the Proj construction you can sort of explain rather than a hand wavy thing like, oh, this is similar to what happens over a field. You can actually explain it by sort of looking at what happens if you take the action of GM on space, which I think is a nice um, viewpoint on it. So what is this useful for? Well, usually at least two things. One is to create projective spaces over arbitrary schemes, and another is to do blowups. So in this video, I'll just be talking about the first thing, so how to create projective spaces over affine schemes, but what I say should be in enough generality that you should see how things play out in general. So let's talk first, sort of classically, not talk about schemes and stuff, about what is Pn of some field k. Um, so for example, if you want, you can take k equals c or r or something. And what this does is it is the space of lines in affine n+1 space over k. So what you do is you take, for example, let's take A2, and let's take the union of all lines going through the origin. No, I should say lines through 0. So pretend like all these lines pass through the origin, even though I'm bad at drawing. And then you sort of pick one representative from each of these lines, and then this gives you your projective space, which is P1. And in general, an+1, if you take the space of lines, you get Pn. Okay, and then, so you want to be able to try this construction in algebraic geometry, so you make some observations. And the observations are that, in algebraic geometry, you want to describe a space in terms of its functions. So you want to understand what the functions on this are. And so what we realize is that subspaces closed, subspaces of Pn are in one-to-one correspondence with, I guess, instead of subspaces, I should say first hyperplanes or hypersurfaces are in one-to-one correspondence with homogeneous polynomials, and this is for hypersurfaces, or homogeneous ideals, and this is for just general subvarieties. And in the variables x1, or I guess x0 up to xn, where x0 through xn are the coordinate variables for an. And the idea is that if you have a zero set, which is a homogeneous polynomial of this, then that'll trace out some cone in an. So if we were working with A3, for example, maybe you trace out this double cone through some homogeneous polynomial, and then this descends to, this is the picture, sort of schematic picture for Pn, and this descends to some subscheme of Pn. And now, since we have something to do with functions and something to do with subspaces, then we can try and generalize this to talk about something in general schemes. And so now we can talk about the Proj of a graded ring. So first I'll give the definition that's usually given, and then I'll talk about how to interpret all this in terms of sort of group actions and how it's actually very similar to this. And the idea is basically that Um, what you're doing is you are removing the origin, and then you are quotienting out by scaling by scalars in your field. So that should be familiar by, for example, taking homogeneous coordinates, which are like x0 up to xn, but then modulo the action of k star, where k star can scale the coordinates. And you also can't have all coordinates being 0. And so the general project construction goes as follows. Let's say that you have a ring R, which is a graded ring. So sum of n greater than or equal to 0 of Rn. And for example, what you can have is if you have some ring S, then you can look at S adjoin x0 up to xn, where the degree of each xi is equal to 1. And so then Sn, which is or I guess in this case Rn, the homogeneous factors of this is going to be equal to the homogeneous degree n polynomials. So R0 will be S, R1 will be linear polynomials in this, R2 will be quadratic polynomials in the xi, and so on and so forth. So the Proj construction says this, that the Proj of R as a set is the set of all prime ideals P, which are inside R, such that P is homogeneous. And so what that means is that P is generated by homogeneous elements. So you can't have something like it's generated by an element of x1 plus x2 squared. So this is not allowed because you have a sum of something in degree 1 plus degree 2. So it has to be generated by things which are homogeneous with respect to whatever grading you put on there. And moreover, P does not contain the so-called irrelevant ideal, which is the sum of Rn for n strictly greater than 0. Okay. And then, so we'll see later that this corresponds to essentially removing the 0 point, the second condition. And as a topology, you say that the closed sets are V of A, where A is some homogeneous element of R. And V of A is defined similarly as just all the homogeneous prime ideals which contain A and satisfy this condition. And then you can also put a sheaf on this, which is you do the following. So what you do is you pick some F, which is homogeneous of degree n, and then you consider the ring R localized at F. And so this is the same thing as R join 1 over F. And what you do is you consider the ring spec of R, F. I'm not sure what the notation is for degree 0, but I'll just put a superscript parentheses 0 for the degree 0 part of this. So R, F degree 0, elements of this will look like the sum of AD over F to the D, where the degree of AD, so AD is some homogeneous element of degree Dn, where n is the degree of F. So this is D times the degree of F. And so what that means is that each of these summands, and thus the full sum in total, will have total degree 0 in this localized ring. And then what you do is you look at spec of this guy, and so this forms an affine scheme. And it turns out that as you vary F, these affine schemes are going to cover Proj R. And because these affine schemes have some structure sheaves on them, you glue those structure sheaves together to get the structure sheaves on Proj R. And the way that you do that is you notice that Rf localized at 0 and Rg localized at 0 for two homogeneous polynomials both map to Rfg localized at 0. And then this corresponds to some affine open, this corresponds to some affine open, this corresponds to some affine open, and this is the intersection of these two. So then you can sort of glue these affine openings together along their intersections, and then that should also produce for you the scheme Proj R. Okay, so this seems like a complicated construction in my opinion. And the first question to ask is like, what does this actually look like? Even for like maybe the simplest example would be say K, a field adjoins some indeterminates. But even for something which isn't a field adjoining some indeterminates, what does it look like? So let's say that you have some space down here, which is spec S. And then let's say that above here you have a proj of S adjoin x0 up to xn. And from now on, so that I won't have to keep rewriting this, I'm going to call this as P and S. So what does this space even look like? Because it's not the same thing as just taking the ideals of this. You're doing this weird thing with homogeneous ideals. So that doesn't account for every single ideal, and you're also considering the ones which don't contain this guy. And so it's not quite clear what the picture for what this should look like even is. And so one thing that you could do is you can sort of probe what the points of this look like by taking one point over here, which corresponds to a map from spec K to this. So spec K is a single point, and this corresponds to the inclusion over here. And this is this corresponds to a map from S down to a field K. And then what you can do is you can look at the fiber above this point. And what you can check is that the fiber actually corresponds to the tensor product, the proj of the tensor product of the string with K. So in other words, the fiber over here will be proj K adjoin x0 to xn. Or in other words, we have P and K. And so this will just be a projective space, just like we've seen over here. And so what that tells you is that the fiber of this point will be some projective space over K. So that means is that as you vary your base points, what you'll get is a family of projective spaces where sort of the field of each projective space will be the residue field of the points of spec S. And the thing is, you can do this not just for closed points, but you can do this for sort of generic or non-closed points as well. And for example, if we look at spec of kt, so taking S to be kt, then we'll have closed points and we'll have a generic point 0. And so if you look at the fibers of the closed points, then you'll get projective spaces over k. But then if you look at the generic point, which will be spec of k bracket t, then what you get is the n space over k bracket t. And so I'm pretty sure what this will look like is this will be like some sort of bigger projective space. And what this will look like is sort of like some sort of a generic projective space which maps down to the generic fiber. And I think you could probably check that if you take the closure of this guy in here, then that should give you the entire space. So it's sort of like a family of projective spaces, not just over the closed points, but over the generic points as well. And they're glued in such a way such that like the closures of generic projective spaces will include the projective spaces of the closed points. Okay, so now that we know somewhat of like what these relative projective spaces look like, maybe we can start with this as motivation and see if we can try and construct a space which will produce this sort of family of projective spaces over spec S, and see if we can actually get this definition of the Proj construction. Okay, so what is the way to do that? Well, what we can do is we can essentially take the initial case that we had over a field and make it relative. So over a field, what we took is we took the space a n plus 1 over the field k. And in this space, we took the space of all lines. And then what we did was we removed the origin and we sort of rescaled, so minus 0, and then modulo k star. So it's sort of a two-step process to get down to projective space. So this will give you P and K. So step 1 is remove 0, and step 2 is scale by k star, or I guess quotient by the scaling. So what should we do in the general case? Well, if we have some spec S, then what we can consider is the affine space um, a n plus 1 S, which will just look like sort of a family of n plus 1 dimensional vector spaces lying over each point. So the fiber of a point over here will be an n-dimensional vector space over the residue field. And so what we can do here is we can do a similar thing where we remove 0 and then scale by k. So what should we mean by removing 0? Well, we can consider that this affine n space is a space with a map down to a single point, and then the 0 point over here corresponds to a section of this projection, and this section takes this point to 0. And so similarly over here, what we can do is we can find a section of this projection which will send spec S to this 0 section in each fiber. And so what we do is we remove the 0 section, so minus 0 section. And then what we'll end up with is this family of vector spaces again, but now with the 0 section removed. And this still maps down to spec S. And what we do now is we have a bunch of lines in these fibers. And what we want to do is somehow figure out how can we quotient out by rescaling. And so when I say rescaling, I mean like you can have like rescaling in each fiber. And what you want to do is identify points within each fiber together if they're off by a scale factor. Okay, so how can you do this? Well, first I should say like you can sort of rephrase these two things. So now the first step should be remove 0. So what that means is remove 0 section of the n plus 1 affine space bundle over S. So you can think of this as an n plus 1 dimensional vector bundle, and every vector bundle comes with a 0 section. And so we want to remove that 0 section first. Okay, and then the second step should be to quotient out by scaling. And so notice that this is scaling by units. And so what will happen here is that we want to quotient by the action, I guess, in action of GM on a n plus 1 S minus the 0 section. And this action should essentially be scaling on fibers. And so I made another video on how you can sort of view GM, actions of GM, and how they correspond to gratings on the ring, and how if you take GM over some relative scheme, then I said a little bit in that video that you can think of it as like a relative picture where you sort of have a GM action over a field on each fiber. And so that's essentially what we're going to do here. Yep. So let's see what each of these two steps should give us. So first off, what is n plus 1 S? This is equal to spec of S adjoin indeterminate variables x0 to xn. And here we aren't going to worry about the grading yet, but just note for later that the grading of each of these will be degree 1, and we'll see why that is in a bit. But first, what is the 0 section of this space? So the inclusion of S into this polynomial ring Sxi gives us the projection of this vector bundle down to our base space. So how do we generate the section of this? Well, we then need a map from Sxi going back to S, which represents the 0 section. And you should be able to convince yourself that this map is the map that takes xi all to 0. And that's because essentially creating a section of this says we should specify some value of xi for every point. and at every point we want xi to be equal to 0. So then this just says that we should just set the xi functions on spec s to identically be 0 for each coordinate. And so what I'll do is that'll create a section for us, which will be the 0 section of this vector bundle. Okay, and then what we want to do is consider this thing, which is an plus 1 minus the 0 section. So what I'll do is I'll call this embedding as z for the 0 section, where z is the map from s into a n plus 1 s. And we want to consider the scheme, which is a n plus 1 s minus z. Okay, so there's one thing which will come back later, which is that this is generally not affine. And for a simple case, the simplest case where this is true is if you look at a to k. So what this is it's just the plane minus the origin. And so I think it's a pretty classic exercise to check that this is not an affine scheme. And the reason for this is because if you look at the global sections of A2K, then this will just be K adjoin x0 comma x1, which if you look at spec of this guy, then you get all of A2K. So this is a picture of A2K minus 0. Sorry, I meant to say spec of A2K minus 0 is equal to this. But if you look at spec of this guy, then you recover all of A2K, not A2K minus 0. So this is a problem because affine schemes are opposite to rings. And so if you take global sections, that should be opposite of taking the spec, but in this case it isn't. And so we conclude that A2K minus 0 is not affine. So what's the point here? The idea is that if it were affine, then this is some subset of A2K. So let's say that this was equal to spec of some hypothetical ring R. Then we have an inclusion of spec R into spec K adjoin x0 comma x1. So what that tells you is that because this is some open set in the sky, this should correspond to some localization of this ring at some function. So we would guess that R should be possibly K join x0, x1 localized at some function f, which is to say that it's a complement of the 0 set of f. But the thing is that what we're doing is we're essentially introducing poles here. So this is K adjoin x0, x1 adjoin 1 over f. And we're only looking at the points at which 1 over f is well defined. Now the thing is, the poles of 1 over f are codimension 1. And you can sort of check that. Like, for example, x squared plus y squared plus z squared equals 1. The 0 set of that is a sphere, instead of just being a discrete set of points. So instead of being instead of being 0-dimensional, it's codimension 1 in your ambient space. So what that means is that if you want to remove some open set from A2, then what you'll be doing is instead of just removing a single point, you'll be removing like a full line from the space. So this is supposed to represent like removing a line from A2. And so you can't invert any function to remove a codimension 2 set, and that's why this thing is an affine. Or said alternatively, that if you know a function defined in enough points, which is to say that like the points surrounding the codimension 2 set, then you can actually fill in what the function should be in the codimension 2 set. And in the complex analytic case, there's a theorem which I think is called Hartog's theorem, which says exactly this, that if you have a function, a holomorphic function, which is defined everywhere except for a codimension 2 or higher set, then you can actually fill in the codimension 2 or higher set with a well-defined value. And so yeah, so the problem is that if we're looking at high-dimensional affine spaces and we remove the 0 set, then generally this is not affine. Okay, so we'll see the consequences of this in a bit. But first, let's talk about the action of GM on this guy. So the action of GM, as we saw, the action of GM on some scheme should be some map from GM cross X to the space X. And let's say that X is affine. So let's say that X is equal to spec A. Then what this corresponds to is a map from A to a tensor. In this case, I guess we're working in the relative setting, but in general, it would be like Z adjoin X comma X inverse, which remember GM is equal to spec of Z X inverse. And so what you can do is that you can rewrite this as a direct sum of a tensor Z to the n. And so what we showed in the last video was that, or in the video discussing the GM actions, is that a map from A to this, which respects the multiplication and whatnot, is equivalent to the data of decomposing A as a direct sum of AN. So the important part over here is that this grading over here is determined by this map F. So this map F, which gives you a map from A to this, in other words, the map which is dual to this guy, which gives you the action, gives you a induced grading on the ring A. So how is this useful? Well, what we can do is we can look at A and S minus the 0 section. So A n plus 1 S minus Z. And we can act on this by sort of, I guess, S star, I'll say. So units on S. And so if this was a field, then what we would be doing is we would be acting on it by the field. And if we can quotient by this action, then the quotient by that action should give us the projective space. So in this case, what we're doing is we're acting on the scheme not quite by S star, but by GM S. And so what that means is that we have a map from GM cross this guy to itself, which gives you an action. And we want to see how can we construct the quotient of this. Yeah. So now I want to talk about how you can sort of categorically talk about quotients of group actions. And we will see that that allows us to give a nice description, similar to how we were able to like find nice descriptions for what an action looks like by looking at things a bit more categorically. So let's say that you have a group, so ignore scheme land for now, and let's say that you just have a group G and some set or topological space or whatever X, and we have some group action alpha on this set X. And we want to ask, so there's a projection map to X mod G, and we want to ask, is there a sort of nice categorical way to think about this projection map down to X mod G? So can we get this X mod G in sort of a categorical fashion given this map alpha? And the answer is yes, and it's quite a nice thing to think about. And the way that you do it is that you actually take a second map of G cross X down to X. And so I guess I should say what you want to do first. So what you want to do is you want to identify down here, so X should map to something, but then every G times X should also map down to something. And so what that says is that if you pull back over here and you look at this composite map, then every pair G comma X should map down to the same thing down in this quotient. But what it maps down to, I guess G comma X should map down to the same point as E comma Gx. And when I say Gx over here, I mean alpha of G times X. And these should map down to the same point down here. So what that says is that we should be looking at all elements of this form mapping down the same thing. And so what we can do is we can look at a second map down here where this projection will take the pair G comma X down to the point X. And this projection over here, we can think about it as taking the point G comma X down to G times X. And we want both of these elements to map down to the same thing. So this is alpha, and this is the second projection. And you can convince yourself that if you look at the co-fiber of this diagram, then this should be the quotient. And again, the reason for that is that what you do is you look at x and you say, okay, let's look at the preimage of x up here, and that will correspond to all pairs g comma x, where g is arbitrary but x is fixed. And then if you look at the map over here under this map alpha, then what that'll do is it'll map this pair to g times x. And so what this being the co-fiber does is it identifies x with g times x for every g in your group G. Okay, so to recap, you have two maps from GM cross x to x, which the first one is given by your action alpha, and the second one is given by your projection down to x. And so again, this should give you the quotient categorically, because if we're working not in schemes, but in just set land, then the preimage of a point x would be all pairs g comma x, and this will map to alpha of g applied to x. And so whatever should be down here should identify x and alpha of g applied to x. So it'll be the quotient. And so if we dualize, if x is affine equal to spec A, then if we dualize things, then what we get is two maps from A down to this ring, alpha star, which is defined by this, which gives some grading on A is equal to the direct sum of an. And over here, this map over here, which corresponds to second projection, which sends every element A to A tensor x0. And so remember from the video on GM actions, we said that the grading sort of corresponds to how much GM scales each function under the pullback of the action. And so what this means is that GM does not scale any function A, which essentially is saying that GM acts trivially on spec A. And you can sort of see that the second projection is also group action, it's just the trivial group action over here. And so the limit of this diagram is the zero graded part under this alpha star map. So this is equal to A0 under this alpha star grading. And again, the reason for that is that both of these guys include into A, and it's exactly what ends up at the same spot over here. Anything else which isn't in A0 but is in A will end up under this map into a higher graded part of this. So then what that means is that the quotient of x under this GM action should be spec of the zero grade part of A under this A star or alpha star. And perhaps you could have guessed this because again, the zero grade part corresponds to all functions which are sort of invariant under units. And so in general, if you take the quotient by a group action, you should look at all functions which are invariant under the group action. And the reason for that is, suppose down here you have some quotient, and up here you have some group action which say permutes these three fibers. Then if you have a function over here, you can pull that back to a function up here, and the function up here will be invariant under the group action because it takes the same value on each fiber. And so you should expect that the functions which define the space down here should be exactly the functions which are left invariant under the group action up here, and that's what we see. Okay, cool. So now let's apply it to the case where x is equal to a n plus 1 s minus the zero section that we had. And if we remember, then this is equal to spec of s adjoin the indeterminates minus the zero section. And so what we can do is we can say, okay, all we have to do is look at the zero grade part of this. And if you look at the zero grade part of s adjoin xi, then that'll just be s. But then we have an issue because spec s is not what we wanted. Remember, what we wanted at the end of the day was to have these vector spaces without the zero section, and then quotient out in each fiber by this scaling action. But if we just look at the zero grade part of this, then we just end up with spec s, And I guess we haven't really done much with the zero section here. And so we see that we have an issue because spec S just gives us the base instead of sort of what we wanted was the quotient, which will give us a family of projective spaces down onto the base. So how can we fix this? Well, the issue is, as I said, this space is not affine. And so what we wanted was to get something which was the colimit of this diagram. And the colimit of this diagram will also work in scheme land, as long as you can find a scheme over here which satisfies this colimit. But the problem is, because we're working with a non-affine scheme, which is this one, um, we can't just dualize and look at the zero grade part of the rings because the category of rings is only opposite to the category of affine schemes. Um, so what that means is that this construction of finding the GM quotient of an affine scheme does not generalize to this case of an plus 1 minus 0 set because minus the 0 locus because, or sorry, the 0 section, because this is not an affine scheme. So how can we fix this? Well, one thing that we can do is we can split X into the union of a bunch of UIs where the UIs are some affine schemes, so spec of AI. And what that means is that this action of GM cross X to X will restrict to an action of GM cross UI to UI. In other words, each of these AIs will be graded. Okay, so how do we um, find these affine opens which will suffice for us? Well, what we can do is we can say that any affine open should be of the form S adjoin xi localized at some function. And the thing is, we want this function to be homogeneous. And the reason that we want it to be homogeneous is because let's say that we look at A2 and we look at, say, the parabola. So this is cut out by y minus x squared, which is not a homogeneous polynomial. Then what happens is we do not get a restriction of the GM action onto this open set, because if we rescale this point out here, we'll rescale it to a point that no longer exists in our space. So what we want to do is consider A2 minus VF, where f is some homogeneous polynomial, so that it'll define some sort of a cone over here. And that way, if we rescale any point, it'll end up at another point which we did not remove from our set. So what that means is that this f should be homogeneous. And moreover, we actually want f to lie inside this ideal I, which is the ideal x0 through xn. And so what is this ideal? So remember what we had was the zero section up here. And the zero section is defined as the map sxi down to s, which sends all the xi to 0. And so the kernel of this map is equal to the direct sum of, or is equal to, on one hand, I, but in the general case for a graded ring, the zero section will be defined by the direct sum of Si for I greater than 0. And so you will recall that when I first described the Proj construction, we had this weird irrelevant ideal, and we can see that the irrelevant ideal exactly corresponds to the functions which define this zero section of our vector bundle over S, or over spec S. So why do we want f to lie inside here? Well, I claim that if f lies inside here, then the zero locus of f, which will look something like this, so you have a bunch of vector spaces, and the zero locus of f will be some family of subspaces in each of these fibers. And I claim that under this condition that f is in I, then the zero locus will be contained inside here. So I mean, maybe you can sort of see that. Another nice way to see it is that we can look at the inclusion of spec of xi localized at f. So that'll be the complement of this zero section. And look at spec of s, which includes into spec x s adjoin xi. And so this will be the zero locus z. And we can look at the fiber over here. And if this fiber is non-empty, then that means that there is still some remnants of the zero section over here, which are not sort of avoided by localizing at f. And so what that'll mean is that in some fiber, for example, maybe you'll have something which looks like this. So this is the zero set of f. It sort of like goes around the zero section. And so if you localize at f, then you still have the zero section. But what we want is to find an affine open cover of this guy, which means that we want to have our affine opens avoid the zero section as well. So if you do this, then what goes up here is spec s tensor s xi localized at f. But remember, this s is defined as s xi modulo the ideal I. So we also have a copy of f inside here. But inside here, the copy of f is 0 because it's inside I, as we proclaimed over here. But over here, f is a unit because we're localizing by it. So then in this tensor product, 1 is equal to 0. So this is just the spec of the zero ring, which is the scheme theoretic and p set. So we see over here that the intersection of these two guys is empty. And so indeed, if we localize at f, we do avoid the zero section. And so we do have that spec of s xi localized at f is contained inside a n plus 1 s minus the zero locus. And moreover, any point which is not on the zero locus will be covered by one of these affine open sets. And the way to see that is there will be some function which vanishes at this point. And because this point is not on the zero locus, you can find some function f inside this ideal I, which vanishes at that point, and then which doesn't vanish at that point. And then you can localize at that function and see that the complement will include this point. Okay, so now we can take the complement of these homogeneous guys and look at the quotient by the GM action. So UI mod GM, and so this will be spec of S adjoin XI localized at F, and the zero grade part of this because of what we have as a description of affine schemes quotiented out by GM. And so we see here that we exactly recover this. So the affine opens that we had over here were generated by R localized at some function, homogeneous function f is at degree 0, or the degree 0 component. And the prime ideals over here were homogeneous primes, which were not contained, which did not contain this ideal Rn. The irrelevant ideal, which is the direct sum of Rn. And so this exactly corresponds to avoiding the zero section. So you can convince yourself that this condition is equivalent to the ideal being disjoint from the zero section. And then the reason that we have a grade ring to begin with is because, remember, the grade ring corresponds to a GM action on X. And then the reason that we take the degree 0 part of this is because we're quotienting out by the GM action on these affine open subsets of your space. And then we can glue these together and recover the projective space that we want to get. And we do indeed get this picture. So I guess one last thing to mention here is that if you change the grading on a ring, then in general it changes the projective scheme. So this is something that I was told, but I didn't quite understand what that meant. But I'll give an example here. So let's say that you look at proj of, let's say, C adjoin x comma y, where the degree of x is 1, the degree of y is 2. So I'll just be using R as a schematic for this. And if you remember from the video on GM actions, we can sort of analyze what the GM action on this is by looking at the preimages of ideals. And so we look at the ideal x minus a, y minus b. Then this gets pulled back to by the unit which corresponds to k in C star. This will pull back to kx minus a, ky minus b, which is to say that x minus a, the point alpha comma beta over here gets sent to the point k alpha k squared beta over here. Okay, so what that means is that the action by scaling on our two-dimensional affine space is not just scaling along the lines, but instead it's this weird scaling which will send some point over here to some point like over here. It'll scale more in the y direction than it does in the x direction. And you can check that the things which are left invariant under the scaling action are not equations of the form like ax plus by plus c, ax plus by equals 0, but instead they will be equations of the form y is equal to some constant times x squared, right? Because that means that x gets scaled by the same amount as, or x squared gets scaled by the same amount as y. So instead of sort of splitting up your affine space into a union of lines, you're instead splitting up into a union of parabolas. And what this action does is it sort of translates along these parabolas. And then if you take the proj of this, then what that's doing is you're removing the 0 section over here, and then you're quotienting out by the scaling action. And so that means is that you have 1 point for each parabola. So you would guess maybe that this still looks like P1 because it seems like you still have sort of 1 point on each parabola on sort of the right half side of the plane. And so maybe we get P1. And one way that we can see that we do is that we can consider the inclusion Cxy into Cxz, where now the degree of x and z is equal to 1. And so you're thinking about the z as sort of being the square root of y, where this map takes y to z, y to z squared. So this is a degree preserving map, and that's to say that it's something which preserves the GM action on both of these spaces. So this has the GM action induced by this grading, which is the usual scaling. This has the weird GM action, which is this sort of parabola scaling. And what we can do is see that this induces a map from P1 to proj C x y. And what is this map? Well, we can sort of look at it at local coordinates. So if we choose the local coordinates where we invert by z, and if we invert by y, then inverting by z, what we'll get is an affine chart which looks like C adjoin x over z. Remember, what we're doing is we're inverting and taking degree 0 functions. And over here, we have C adjoin x squared over y. And so again, that's because y is degree 2. So if we invert by y and then take degree 0 components, then we essentially get polynomials in x squared over y. And we have a map over here. And what this map does is, let's call this generator u, and let's call this generator v. Well, it takes x squared over y to x squared over z squared, so this will take u to v squared. And so what that means is that it'll induce a map from P1 to this space, which is going to also be P1, and it's the multiplication by 2 map. So it's the, if we sort of draw the complex picture, then it'll be the one that rotates by 2 along the z-axis and identifies the points as such. And so in this case, we do still end up with P1, but you can imagine that if you go to higher dimensional projective space and you sort of start messing around with the gradings over here, then what will happen is in general you get some quotient of Pn. And because the structure of higher dimensional spaces is more interesting, you might get non-trivial quotients of Pn. And that's why if you take Proj of things where not everything is degree 1, then even though it's the same variables that give you projective n space, you might not end up with projective n space, but rather some quotient of it.